We are continuing part 3 of the slides, and here we are doing an example of unconstrained optimization, and you are told to find and classify the stationary points of the function z is equal to 1000x plus 800y minus 2x squared minus 2xy minus y squared. So in order to solve this optimization problem, you first need to find your first and second order partial derivatives. So these two are your first order partial derivatives, and these over here are your second order partial derivatives. So this is dz by dx, partial dz by dx. So getting your first order partial of this function z with respect to x, treating y as a constant. That is the answer, but let's look at how we got it. So if I differentiate every term where I see an x, I'm going to get, if I start with this first term, my exponent is 1. So 1 times 1000 is 1000, and x is now raised to the power of 0, and anything raised to the power of 0 is just 1, so it's just 1000. This term over here has a y, so we know that anything that has a y we're going to treat as a constant, so this will differentiate to 0. Here we have an x, so I'm going to differentiate this term. So I've got 2 times minus 2 is going to give me minus 4. And then I have x to the power of 2 minus 1, so it's just x to the power of 1. Here I have a constant multiple, so I'm going to take my power of x and differentiate that. So I've got 1 times minus 2 is minus 2. But now x is raised to the power of 0. So that is just 1. So I still have minus 2. But I still have this y. And because it's a constant multiple, that doesn't fall away. So I'm left with minus 2y. And this will differentiate to 0. So remember, we differentiated this function with respect to x, treating the y as constant. So they'll differentiate to 0. So next, we're going to differentiate the function z with respect to y, treating x as a constant. So if I differentiate this term, of course, if I'm going to differentiate this with respect to y, this will differentiate to 0. Here, if I differentiate this term, I'm differentiating with respect to y. So I have 1 times 800. I'm going to have 800 times y raised to the power of 0, and y raised to the power of 0 is just 1. So hence that is just 800 times 1, which is 800. Here I've got a term that only has x, so I treat that as a constant and it will differentiate to 0. Here I have a constant multiple, so the y has a power of 1, so if I differentiate that, it's going to be 1 times minus 2 times x, y raised to the power of 0, so I'm left with minus 2x. And here, if I differentiate that, I've got minus 2y. So we now have our first order partial derivatives with respect to x and with respect to y, respectively. Next, we need to get our second order partial derivatives. And you can see with this second order direct partial derivative, I've taken this first order partial derivative and I've differentiated this again with respect to x. So if I differentiate this with respect to x, what do I end up with? Simply minus 4. And that is why it's referred to as a direct second order partial derivative, because I'm differentiating this first order partial with respect to x again with respect to x. Now, if I get my second order partial derivative or my direct second order partial derivative with respect to y, I go to the first order partial derivative with respect to y, and I'm going to differentiate this again, but again with respect to y. So these get treated as constants, they differentiate to 0. And if I differentiate this with respect to y, I'm simply left with the constant minus 2. Now here's an interesting thing. I only have one cross partial over here. And the reason being is when you get your cross partials, you would first differentiate the function. You'll get your first order derivative and differentiate that with respect to x. Then you're going to differentiate this a second time, but now with respect to y. So if you differentiate this now with respect to y, you can see you're going to get minus 2. But let's have a look at if we were to get the cross partial where we differentiate this first order partial derivative that was with respect to y, but we differentiate it now with respect to x. You'll see you also get minus 2. So you don't deal with it here, perhaps in a pure math course you'd hear about Young's theorem where your cross partials are always going to be the same. So you have just got one cross partial because both cross partials are in fact minus 2. So that is your first step. The second step now is to solve by simultaneous equations. So first you are going to set your first order derivatives equal to 0. So if we set our first order partial derivative with respect to x, which we got, equal to 0, we now can rearrange to get y is equal to 500 minus 2x. So that is just making y the subject of the formula. Next, we have our first order partial derivative with respect to y. This is a typo, so this should be y. So this is your first order partial derivative with respect to y, which you got in your previous slide. And that we set it equal to 0. So now we want to solve by simultaneous equations. So if I'm going to take these two terms over to the other side, therefore 800 is equal to 2x plus 2. But we saw that y, by rearranging this first order partial derivative, when we set it equal to 0, y was equal to 500 minus 2x. We can now substitute that in over here. Now we only have one unknown, that is x. So now if we multiply out, we have 800 is equal to 2x plus 2 times 500 is 1000. Positive times a negative is negative. 2 times 2 is 4x. So now we're going to have, we can solve for x. So if we take our x's over, we're going to have minus 2x plus 4x. That is going to give us 2x, and 800 becomes minus 800 on the right hand side. So 1000 minus 800 gives us 200. So means x is just going to be equal to 200 divided by 2. X is equal to 100. And now you can substitute that into your function over here where y was equal to 500 minus 2x, and x is 100. So y is equal to 300. So we've solved for our values for x and y. But now we have the coordinates, but remember we want to evaluate the nature of this point. So now we need to look at our second order partial derivatives. So the nature of the stationary point, remember we already got our second order partial derivatives in step 1, and you saw that your second order direct partial derivative with respect to x was minus 4, and your direct second order partial derivative with respect to y was minus 2. So both here are negative. And now if we look at the product of our direct second order partial derivatives, that is minus 2 times minus 4 over there. That is the product of those two direct second order partial derivatives minus the square of our cross partial, and our cross partial was found to be minus 2, so minus 2 squared, we get 4, and 4 is greater than 0. So remember the conditions previously in part 2. We saw that if we evaluate our direct second order partial derivatives and they are both negative, but this condition over here is greater than 0, then we have a relative maximum point. So hence we can evaluate that at x equal to 100 and y equal to 300, it is a stationary point that leads to the maximization of z. Now, this is all well and good, but we want to see how it would be applied in economics. So let's look at our next problem. Now, here we go. We've got a firm producing two goods, X and Y, and the profit function is given as profit is equal to 480 x minus x squared plus 340y minus 1.5y squared minus 50,000. So this calculate the profit maximizing quantities of x and y and the maximum profit. Check your first and second order conditions. So here's an application. So your first step is to derive the first and second order partial derivative. So I'm going to go a bit quicker now. So your first order partial derivative with respect to x holding y constant is simply going to be 480 minus 2x over there, and these get treated as constants. Now your first order partial derivative with respect to y of this function, treating x as a constant, we treat those two terms as constants and they differentiate to 0. So if I differentiate these with respect to y, I'm going to get 340 minus 3y. And that is that first order partial derivative. Now if we get our second order partial derivatives, here we have our direct second order partial derivative. So I'm going to differentiate it, our first order partial with respect to x a second time, but with respect to x, I'm going to get minus 2, and that is that direct second order partial derivative. And if I differentiate this first order partial derivative with respect to y again with respect to y, I'm going to get minus 3. And if I want to obtain my cross partials, I can take any one of these and say, right, I've differentiated this with respect to x. Now let's differentiate this with respect to y, and I can see I'm going to get 0. Similarly, here we differentiated first with respect to y, but if we're going to differentiate this with respect to x now to get our cross partial, again, it's going to give us 0. So that is our step 1. Step 2. Next, we are going to set our first order partial derivatives equal to 0. So here's our first order partial derivative with respect to x, which was 480 minus 2x. So if I set it equal to 0, I can solve for x, and x is going to be equal to 240. If I take the 2x over, it becomes positive, and 480 divided by 2 is simply 240. Here we have our partial derivative, first order partial derivative with respect to y. This is again a typo. So this should be y. And if we set this equal to 0 and we take the 3y over, it becomes positive. Hence, y is simply going to be 340 divided by 3. Y is equal to 113 and a third. So what is our final step? We need to evaluate that stationary point. So if we look at our second order conditions, our direct second order partial derivatives with respect to x, we saw that it was minus 2 and that is negative, and with respect to y it's minus 3 and that is also negative. And the final condition is that we need to get the product of these two direct partial derivatives minus the square of the cross partial, which was 0, and evaluate if it is greater or less than 0. And in this instance, it is 6, it is greater than 0. So hence, these conditions hold for a relative maximum point. So remember the question asked that you need to determine the quantities of x and y that would lead to a maximization of profit. Well, you've determined that x was equal to 240 and y was equal to 340 over 3, and that is in fact the quantities or the stationary point leading to the maximization of profit. And we know that it is a relative maximum given by these conditions, that our direct second order partial derivatives, these two are negative, and that this condition is positive. So that is a relative maximum. Lastly, the final question asks that you determine what that maximum profit is. So the maximum profit, you are going to substitute your value for x and your value for y into your original profit function. And if you substitute these values, you will be able to solve for what that maximum profit would be. So this is an example of an unconstrained optimization problem. So your to-do list is to complete these 3 exercises. So please complete these 3 exercises and I will provide the answers on a Canva in this week. This concludes the work done for week 3 and topic 2, namely partial differentiation and unconstrained optimization. We will continue next week with constrained optimization, focusing on consumer equilibrium that relates to the work that you are doing this week in microeconomics ECO 231. Thank you.